Okay, so for our final example for today, what we're going to look at is another example of functions as inputs to another function. So let's write the two. So like the best way to think about these higher order functions or functions as input is you take two similar but not quite identical looking pieces of code, and then you look at the differences between them, and then you add enough inputs to make a more general version that encompasses both of them. So let's just say we've got a function even p, which says, is x even, and returns a bool. And we wrote this out by recursion once upon a time, but now we can say that it's true if and only if x mod 2 is equal to 0. Given that, we can write a function that says, given L, which is a list of numbers, we can return a bool. And what we'll do is we'll ask, is there an even number in the list? Well, if L is empty, is there an even number in the list? No. And if L is x times x's, then if x is even, then the answer is true. And if x is not even, then what we have to do is we have to ask, is there an even number in the rest of the list? Okay, so now, for example, the list 135 doesn't have an even number, but the one list 1352 does have an even number. We can simplify things a little because this pattern of case even px of if it's true, then true, otherwise has even x's actually has a name, which is that what we're saying is even p of x, or else has even of x's. So that's just another SML notation for exactly the same thing, or else is a Boolean and it takes two Boolean expressions. In this case, is x even, or does x's have an even? And it returns true if one of them returns true and returns false otherwise. Okay, so that's example one. Example two is, let's say, I don't know, has an A where we have L, which is a string list, returns a bool. Case L of, if the list is empty, then it doesn't have an A in it. If it's x times x's, then we want to ask, is x equal to the string A? Or else, is there an A in x's? So for example, has A of A, B is false, but has A of A, B, A is true. So these look very similar, right? In both of them, we take a list, we open up the list. If it's empty, the list is empty, the answer is false. If the list has a first thing and some more stuff, then we ask a question about the first thing and or that with recurring on the tail. So if we try to write a general pattern here, what we should think about is writing a function that takes in something and L, which is a something list, and returns something. Well, if we look at these two functions, both of them return a bool. Okay, so we'll return a bool. If we look at these two functions, has even takes in an int list, has an A in it, returns a string list, and so these two differ. So let's put in a variable here and say that takes a something list, an A list. And then we can kind of copy in the bits of the code that are the same between the two of them because we're abstracting this pattern of computation. And notice that in both of them, what we do is we do something for the first bit, and if that fails, then we make a recursive call on x's. So now what we need to think about is what we put here, and the thing that goes here is like ask a question about x. And so in has even, the question that we ask about x is x even? And in has a, the question we ask about x is x equal to a? And so we want a placeholder that stands for that question that we ask about x. So what goes here is an input to exist that has a function type, right? And all semester we've been notating the function type, like, for example, in the handouts that describe the problems, that said something like, write a function that takes an int to a string. Well, the way we wrote that was int arrow string like that. The only new thing here is that we're allowing ourselves to use the function type as the input position to another function. Well, what do we need to do? We need to say what the domain or the input to the function is, and we need to say what the range or codomain or output of the function is there. Well, what's the domain of it? If we're going to go through and apply Q to each element of L, and L contains A's, then the input to Q is supposed to be an A. And if we're doing an or else to combine this question's answer true or false with this question's answer true or false, then the output of Q had better be a bool, like that. Okay, so then the only thing we've got left to do is to figure out what goes here. Well, we want to keep asking the same question about Q in the recursive calls. So what goes there is the same Q. And so now the point of all of this is that I can take has even and has a. Well, right, those were specific instances of this pattern of exists. In particular, has even, we can get rid of the code for that because it's really just, does there exists an even number in L? Has even of 1, 2, 3 will be true, and has even of 1, 3 will be false. And has a, what's that? Well, it exists of something in L. But in this case, we don't have a name for the is it equal to a specifically. So we can write that as an anonymous function, the function that sends x to ask if x is equal to capital A. And then has a of a, b, c will be true, has a of b, c, a will be true, has a of b, c will be false. Okay, so what we've done is we've simplified the code by saying we don't need to write these out specifically because they're really two instances of the same general pattern. And now that we've codified the pattern using what's called a function as input here, that's one thing we're using here. And we're also using what we call polymorphism, right? To say that exist can work on an A or a bool and an A list giving you back a bool. In particular, that means if you have a list of strings, ints, and you have an int question, like even p, you can do it. If you have a list of strings and you have a string question, like is it equal to the string A, then you can do it there. Okay, so that's another example of taking a different pattern of computation and rendering it as a higher order function, right? So this isn't quite the same as math, right? When we did math, what we did was we had a function that took a this to a that, and then we lifted that to a function that takes a this list and gives you back a that list. When we do exists, it's a different template or a different pattern of computation. Here we have a question like a function that goes from a to bool, and then we have L, which is a list of A's, and we're returning a bool. So like you can't get exists from map or get map from exists because they're capturing two different patterns of computation that do something slightly differently, but they're both sort of general patterns of computation in the sense that the specific question that you're asking in exists, like is the number even or is the string A, doesn't show up, right? It's more abstract than that. Instead, it says, whatever question you want to ask, I'll go through and ask that question of each element of the list, collect up the results, and tell you whether one of them was true. So in lab tomorrow, what you're going to look at is taking some other patterns of computation and turning them into templates like this, turning them into higher order functions. And then what we'll talk about in class on Wednesday is writing code by kind of chaining together different bits of computation given by instantiating different higher order functions. So you can start to think about, like, rather than writing a helper function, you just pull a template, a higher order function off the shelf, instantiate it to do what you want, and then put a bunch of those bits together to get a whole program. So we'll look at different ways of doing what's called functional decomposition of problems, decomposing a problem into a pipeline of higher order functions, instances of higher order functions chained together. And that's a lot more succinct, a much more succinct way to write code than we've seen so far. Okay, so that's what's coming up. Talk to you later. Bye.